Here's a question. What does a real cipher actually look like under the hood? I don't mean a box labelled Encrypt on a diagram somewhere. I mean the actual algorithm, working bit by bit. In this lesson, we're going to encrypt a message by hand, and every permutation, every lookup table, and every XOR will be shown on screen. The cipher we'll use is called SDES, the Simplified Data Encryption Standard. It has the same structure as a real DES, which protected banking traffic for decades. It has a key schedule, Feistel rounds, S boxes, and permutations, but the numbers are small enough to follow by hand. By the end, you'll understand DES not just at the diagram level, but down at the level of individual bits. Because the full cipher is really the same machine, just running on bigger numbers. Before we trace anything, there are two terms we need to establish because they frame everything that follows. Every cipher we've studied so far, from Caesar through Visionaire to the one-time pad, encrypts and decrypts with the same key. That's called symmetric encryption, and DES and SDES are both symmetric. The same key that locks a message also unlocks it, and the algorithm runs the same circuit in both directions. We've been working with this model all along, we just hadn't given it a name until now. The second term is the distinction between stream and block ciphers. Remember that the one-time pad worked one bit at a time. That makes it a stream cipher. Each plaintext bit is XORed with exactly one key bit, and only when that's done does a cipher move on to the next. SDES, on the other hand, is a block cipher, and the difference is exactly what it sounds like. All 8 bits enter the cipher together, they get mixed inside, and all 8 bits of ciphertext emerge at the same time. The whole block is processed at once. So stream ciphers process data bit by bit, while block ciphers take the whole chunk at once. SDES works on 8-bit blocks, the real DES works on 64. Here's our setup for the rest of the lesson. The plaintext is 11110000, a single 8-bit block. The key is 10 bits long, 1010000010. From these 10 bits, the key schedule will produce 2 different round keys. And the ciphertext is 8 bits we don't know yet. That's what we're about to compute. One thing worth saying out loud is that the algorithm itself is completely public. Every table we're about to use is in the published specification. The key is the only secret. Here's the whole machine at a glance, before we take it apart piece by piece. The plaintext enters at the left and immediately passes through IP, the initial permutation, which is a fixed shuffle of all 8 bits. Then comes the heart of the cipher, 2 Feistel rounds, called FK1 and FK2, with a swap of the half blocks between them. That swap is the SW step. On the way out, IP inverse undoes the opening shuffle, and what drops out is the ciphertext. Each round needs its own key. Those come from the key schedule, which stretches and slices the 10-bit master key into K1 and K2. So that's the map, and we'll walk it left to right. We start with the key schedule because the rounds can't run without their keys. The key schedule has one job, which is to turn one 10-bit key into 2 8-bit round keys. Here's our master key again, 1010000010. Each position is numbered from 1 to 10, and those numbers matter because permutations move bits by position rather than by value. The first step is P10, which is a fixed shuffle of all 10 bits. The table says that position 3 moves to slot 1, position 5 moves to slot 2, and so on for all 10. Nothing's discarded yet, every bit just changes seats. Now we split the shuffled key down the middle. The left 5 bits become C0 and the right 5 become D0. Next, each half rotates left by 1 position. It's a circular shift, so the bit that falls off the left end wraps around to the back. Watch what happens to C. 10000 becomes 00001, with the leading 1 wrapping around to the back. D does the same thing independently. Now we treat C1 and D1 as a single 10-bit string. P8 picks 8 of those 10 positions and shuffles them. 2 positions, the first 2, don't make the cut, they're simply dropped. The 8 bits that survive, rearranged, become one first round key. K1 is 10100100. K2 starts from the same place, C1 and D1, so there's no need to redo P10. This time, each half rotates left by 2 positions. C1, which was 00001, becomes 00100. Then we apply P8 again, with the same selection and the same drop. The bits have moved though, so the output is different. K2 is 01000011. And that's the key schedule done. We have 2 round keys, each one a different window into the same 10 bits. Now we can pick up the plaintext. With the round keys in hand, we can start encrypting. Our plaintext is 11110000. The same drawer as the key applies. We number the positions because IP moves bits by position. IP shuffles all 8 bits. Bit 2 moves to slot 1, bit 6 moves to slot 2, and so on down the table, giving us 10111000. Does this shuffle add any security? Honestly, no. It's a leftover from the way 1970s hardware loaded data, but it's in the specification, so we follow it. We split the result down the middle. The left half, L0, is 1011, and the right half, R0, is 1000. These halves are the inputs to round 1. Now for round 1. The first thing we do is park the left half. L0 waits on the side while the right half does all the work. The Feistel function f takes 2 inputs, the right half, R0, and the first round key, K1. But notice there's a size mismatch. R0 is 4 bits, while K1 is 8, so before they can mix, R0 needs stretching. The expansion permutation EP does that stretching by reusing bits. Watch each input bit split into 2 copies, which land in 2 different output slots. So 4 bits go in and 8 bits come out. There's no new information, it's just the same bit spread wider, but now the widths match. We XOR with K1, which is the same move that one-time pad made. Matching bits give 0, and differing bits give 1. The result is 11100101. We split it in half, sending the left 4 bits to S-box 0 and the right 4 to S-box 1. That brings us to the S-boxes, short for substitution boxes, the cryptographic heart of this cipher. Each is a tiny lookup table taking 4 bits in and giving 2 bits out. Fair warning, this lookup is the fiddliest step in the whole algorithm, so we'll go slowly. S-box 0 receives 1110. The 2 outer bits, the first and the last, pick the row. Ours are 1 and 0, which is binary for 2, so we're in row 2. The 2 inner bits pick the column. Ours are 1 and 1, which is binary for 3, so we're in column 3. We look up row 2, column 3, and the table says 1, 1. That's the output of S-box 0. The second group, 0101, goes through S-box 1. It's the same procedure, just a different table. The outer bits are 0 and 1, which put us in row 1, and the inner bits are 1 and 0, which puts us in column 2. The entry there is 0, 1. We glue the 2 outputs together, 1, 1 followed by 0, 1, and we're back to 4 bits, 1, 1, 0, 1. Here's why these little tables matter. The mapping is a lookup, not a formula. Notice the table is also destructive. 4 bits go in, only 2 come out. In S-box 0, 5 different inputs all produce 1, 1, so the output hides what went in. The deeper strength is what a lookup denies an attacker. When the one-time pad's key was reused, XOR's formula let us combine 2 ciphertexts, and the key cancelled out. A lookup gives no such formula. There's nothing to rearrange and nothing to cancel. That's what non-linear really means, and it's where the cipher's strength lives. Back outside the boxes, the 4 S-box bits take one last shuffle, called P4, where bit 2 moves to slot 1, bit 4 to slot 2, and so on. With these particular bits, the result happens to look identical, 1101. That's pure coincidence though. The rewiring is real. L0 comes off the bench. We XOR it with F's output. 1011 XOR 1101 gives 0110. That becomes our new left half, L1. Meanwhile, R0 rides through untouched and becomes R1. The structure is lopsided on purpose. That asymmetry is what lets decryption undo everything, as we'll see. That completes round 1. On the left we hold L1, 0110, and on the right R1, 1000. Between the 2 rounds sits the swap step, SW, where the 2 halves simply trade places. So round 2 will see 1000 on the left and 0110 on the right, It's the same machine again, just with new inputs. Round 2 runs the same Feistel function with the same EP, the same S boxes, and the same P4. Only two things have changed, the block and the key. EP stretches the new right half, 0110, out to 8 bits, giving 00111100. This time we XOR with K2, and the result is 01111111. Into the S boxes again. S box 0 receives 0111. The outer bits put us in row 1, the inner bits in column 3, and the output is 00. S box 1 receives 1111. The outer bits put us in row 3, the inner bits in column 3, and the output is 11. We stitch those together to get 0011, and P4 shuffles that into 0110. That's the output of F for round 2. We XOR with the left half, so 1000 XOR 0110 gives 1110, which is L2. The right half passes through as R20110. And notice there's no swap this time. SW lives between the rounds, not after the last one. Our block now stands at 11100110, and we're one step away from the ciphertext. The last step is IP inverse, the mirror of the shuffle we started with. Every bit returns to the seat it was originally taken from, and out drops the ciphertext 01101101. 8 bits went in, 8 bits came out, and every intermediate value sat on screen along the way. You can rerun the whole thing on paper and check us. Before we move on, look at what happened to any single plaintext bit. It went through the S boxes, was spread by P4, crossed the boundary at the swap, and then hit the S boxes again. By the end, every ciphertext bit depends on every plaintext bit, and every key bit, and none of those paths are straight lines. That has a name. 2 names, actually. They're called confusion and diffusion, and they're Shannon's 2 requirements for a practical cipher. Claude Shannon, the same Shannon who proved the one-time pad perfectly secret, set out in 1949 what a practical cipher needs instead. He named 2 properties. Confusion means tangling the relationship between the key and the ciphertext until no shortcut survives. In SDES, confusion is the job of the S boxes, because they're nonlinear lookups with no formula behind them. Diffusion means spreading each bit's influence as wide as possible, so that any pattern in the plaintext dissolves. Diffusion comes from the movers. EP and P4 spread bits around, and the swap carries influence across the half boundary between rounds. When you put the 2 together, you get something you can actually watch happen. It's called the avalanche effect. Here's the pair we just computed, the plaintext and its ciphertext. Now we flip a single plaintext bit, just the first one. We encrypt again with the same key and the same tables, and the new ciphertext is 11001011. If you line them up, 4 of the 8 bits are flipped. Half the ciphertext changed because of 1 flipped input bit. And that's with only 2 rounds. The real DES runs 16, and if you flip any input bit there, on average half of all 64 output bits change. One honest note before we decrypt. IP and IP inverse contribute nothing to any of this. They're cryptographically inert, that hardware left over from earlier. The S boxes, EP, P4, and the swap sitting in the middle of the pipeline do all the real work. So we can lock the box. Can we unlock it? Decryption reuses the entire circuit, the same IP, the same Feistel function, the same S-box tables, and the same IP inverse. Only one thing changes, and that's the key order. K2 feeds the first round now, and K1 feeds the second. Why does that unwind everything? Well, look at what F's output actually does. It never overwrites anything. It's only ever XOR'd onto one half, while the other half passes through untouched. And XOR is self-cancelling. If you apply the same value twice, it vanishes. Reversing the key order lines each XOR up with its twin, and the twins cancel. So we run it. The ciphertext goes in, K2 is applied first, and then K1, and the plaintext drops out, 11110000, recovered exactly. And that's SDES from end to end. So how far is this from the real thing? SDES is a teaching cipher. published by Ed Schaefer in 1996 precisely so that students could trace every bit, the way we just did. The real DES became a United States federal standard back in 1977, and it's this same blueprint at full size. It uses 64-bit blocks instead of 8 and a 64-bit key, of which 56 bits are effective instead of 10. It runs 16 rounds instead of 2, and each round is fed by its own 48-bit round key. It has 8 S boxes instead of 2. They're bigger tables, taking 6 bits in and giving 4 out, but it's the same row and column lookup you just did by hand. And the bottom row is the finisher. Both are Feistel networks with an identical skeleton. The keys schedule permutes, splits, shifts, and selects. Each round expands, XORs with the round key, substitutes, permutes, and XORs the other half. You've already run every one of those moves. So the next time you see the DES block diagram, you'll know what's inside every box, down to the individual bits. It's the same algorithm at a different scale. If you want the rest of this cryptography course, hit subscribe so YouTube tells you when the next lesson drops, and a like on the way out helps other learners find it.